The University of Arizona Facilities Management Utility Heating and Cooling Department provides approximately 3 billion refrigeration tons per year towards the university's instructional and research facilities, housing, hospitals, athletic facilities, and other locations across campus. For the 2019 fiscal year, facilities management estimated spendings of nearly $55 million, with a large percentage spent by the utility heating and cooling plants. The heating and cooling plants consist of three facilities: AHSC, CRB, and CHRP, with a total of 18 industrial chillers and 4 thermal energy storage units, varying in specifications such as capacity, min and max evaporator and condenser flow rate, header configurations, and other elements. Currently, operators at each of the three plants use historical heat duty trends and heuristic procedures to predict the energy demand and find optimal process configurations in response to heat duty. The Utility Heating and Cooling Department has asked us to find a mathematical and quantitative approach to these procedures by creating a cooling load forecasting algorithm using novel machine learning techniques, reduce overall chilled water energy usage by optimizing the chiller system across the three facilities, and document all programming procedures and organize scripts such that it is easily accessible to operators.
The Chirp AI system is organized into unique modules that function independently of downstream elements. Each module is implemented as a class in Python, where pertinent metadata and operational methods can be called. There are two main sections of the Chirp AI system. The first subsystem predicts cooling demand with a selection of data streams, a neural network prediction model, and a quality assurance module. The second subsystem finds the optimal chiller settings using a Lagrangian optimization with consideration for chiller efficiency curves, equipment limitations, and the system provides a CSV of hourly chiller settings with an estimated operating cost rate and flags for any downstream errors. A preloaded model can make predictions in about 7 to 10 minutes on a system with CPU computation only. Inputting data streams are fed into the model. Each data stream runs a line that forms polls into system-compliant data structures, cleans up formatting, and checks for any predefined data issues. Chirp AI has implemented a neural network trained on past load and feature data to predict future cooling demand. The data is carefully split into training and testing sets. This allows the model to be fairly evaluated on provided data without any overfitting during training. In order to expedite model training time, Chirp AI utilized Amazon's cloud computing platform. With this AWS EC2 instance, a GPU-connected TensorFlow was capable of reducing training times from matters of days to hours. In 2017, China's State Grid Energy Research Organization published a neural architecture that substantially outperformed all other traditional prediction models. From this paper, we found that the convolutional layering with varied kernel sizes and max pooling was effective in processing the minute-leaf features for similar to He's suggested LSTM, averaging the hidden states of a gated recurrent unit was relatively successful in aggregating the convolutional results. Chirp AI also found that residual layering provided substantial increases in performance novel to previous research in cooling demand forecasting. By adding the previous day's demand to the model output, the neural network is only required to approximate the relative changes from the previous day's demand. The range of predictions is vastly decreased with this novel method, as the magnitude is now given by the previous day's load. This reduced the error of the University of Arizona's cooling, and we would expect that the results would be similar for other demand prediction problems.
The Lagrangian multiplier was used as our mathematical model to optimize the overall chiller system across the three facilities. A Lagrangian multiplier is a mathematical strategy that seeks the local minimum or maximum of a function given various constraints. For our system, the target function is the sum of individual chiller COP, the coefficient of performance, which is the required kilowatt of energy necessary to produce 1 ton of cooling as a function of PLR, or part load ratio, essentially the operational power setting. This relationship was sought out since PLR versus COP shows characteristics while easily satisfying operational constraints and having obtainable regression constants using a second-degree polynomial. The constraint for our Lagrangian model is the cooling load CL from our predictions made by our neural model equal to the sum of the individual chiller's loads PLR times RT, while satisfying the minimum and maximum chiller thresholds such as flow rate and maximum capacity. The Lagrange algorithm inputs various parameters such as differential temperature and predicted cooling loads, which then get applied to the Lagrange multiplier lambda. Lambda is used to find individual chiller PLR and is converted into flow rate. If the flow rate and PLR values of individual chillers satisfy the operating limitation, then PLR values are converted to differential pressure for operation accessibility and total energy usage is logged.
Now we will discuss the results from the project. First, we highlight the second-order regressions between the coefficient of performance and bill. On the left is a plot of the regression for one chiller, in this case, AHSC Chiller 2. On the right is a plot that contains a regression for all 18 of the applicable chillers. It is known that these two features of chillers generally share an approximately quadratic relationship. Because of the nature of how central facilities typically runs equipment, much of the data was concentrated in the PLR range between 0.5 and 1. In order to counteract this issue, a sample size of 200 randomly selected points was chosen to perform the regression calculations. The sample points were chosen from a uniform distribution across the PLR range of the data. Because the points are chosen uniformly, the regression is able to capture the true shape of the efficiency curve for each chiller because all intervals in the PLR range are equally represented. The results of these regressions are utilized in the Lagrangian optimizer to relate an optimal coefficient of performance back into an operator-usable PLR value. Next, we see an overlay of the actual campus demand, predictions of the campus demand from our neural network model. The plot on the left shows the full prediction range from April 2018 to January 2020. The plot on the right shows the neural network predictions from 1 month, May 2019. We can see that our neural network captures the trends in cooling demand from campus, indicating that our model is working in an ideal fashion with errors of only around 10%. This result can be improved as more data from central facilities is available for the neural network to learn from.
Lastly is a cost comparison between how much the university actually spent on the chilled water system versus what would have been spent if our algorithm had been employed. The time frame of interest is about 900 hours between February 12, 2019 and February 12, 2020. As can be seen, the algorithm would have potentially saved over $2,300 during this time span. This correlates to annual savings for the university of nearly $22,500. In conclusion, the Chirp AI team has thoroughly studied the central facility's chilled water distribution system and its operation, and trained a neural network model that successfully predicts the cooling demand on campus within 10%. The team also developed an algorithm that determines an optimal chiller configuration to most efficiently meet this demand, both of which are novel methods for facilities management. This model is robust in nature and has built-in measures to account for unreliable data, breaks in data streams, offline chillers, events on campus, and operator usability. We believe that the use of our algorithm, alongside the current strategies employed by facilities management, has the potential to save the University of Arizona tens of thousands of dollars every year